What if a distant object entering our solar system wasn't behaving like anything we've ever studied before, and the data we rely on to understand it was pointing to something far more organized than random natural processes should allow? On March 29, 2026, at 1842 UTC, a signal recorded by NASA's Deep Space Network antenna DSS-43 in Canberra began to raise exactly that kind of question, as it appeared to capture activity from the interstellar object known as 3I, Atlas, that did not match expected cometary behavior. The initial interpretation of this event came from a statistical standpoint. Based on the data logs, the likelihood of this emission pattern being a naturally occurring cometary outgassing event was estimated to be extremely low, around 0.02%. What stood out was not just the presence of particle emission, but the structure of that emission. Instead of a chaotic spread of material, which is what scientists typically observe when solar heating causes sublimation of volatile compounds, the recorded signal suggested a highly coherent and organized stream of particles. This distinction matters because natural processes tend to produce dispersion, not precision. At the time of detection, the object was still positioned approximately 187 million kilometers from Earth, moving through interstellar space on a trajectory that has already been classified by multiple astronomical institutions as consistent with an incoming interstellar comet. Under normal conditions, such objects develop a coma as they approach the Sun, shedding material in irregular, expanding clouds. However, the data associated with 3I, Atlas, indicated something very different. Instead of a diffuse cloud, the emission appeared to form a tightly focused stream aligned along a specific vector that intersected the orbital plane near Earth's path. This kind of directional emission is not typically associated with passive thermal processes. The precision implied by the alignment suggested a level of control or structure that is not accounted for in standard cometary models. In natural scenarios, any material released from a comet's surface would expand radially due to pressure differences and the vacuum of space, dispersing in all directions rather than maintaining a narrow, directed path. Yet the observations indicated that the deviation of this stream was less than 0.03 degrees over vast distances, a level of coherence that is difficult to reconcile with known natural mechanisms. Independent observations contributed additional context. Data from the ALMA Observatory in Chile showed a dense, continuous structure within the particle stream. Under certain atmospheric and observational conditions, some reports even suggested that the stream could be faintly visible from Earth-based instruments as a thin thread of material stretching across the background of space. While such visibility is rare, it reinforced the idea that the emission was not only present but sustained and structured over long distances. To evaluate these findings, scientists compared the observed behavior with established models of cometary physics. In a typical comet, solar radiation heats the surface, causing volatile compounds to sublimate and escape in an expanding, turbulent flow. This process produces a coma and often a tail that points away from the Sun due to solar-wind interaction. However, the emission from 3I, Atlas, did not match this pattern. Instead of expanding outward, the stream maintained a narrow cylindrical profile, suggesting confinement rather than dispersion. This observation led researchers to consider whether any known physical mechanisms could account for such confinement. In laboratory settings, directed particle beams can be maintained using magnetic fields which guide ionized particles along a defined messier. However, such systems require controlled environments and sustained energy input, conditions not typically associated with natural celestial bodies. The implication is that maintaining a coherent plasma stream across such vast distances would require a mechanism capable of counteracting the natural tendency of particles to disperse in a vacuum. As multiple data sources converged on the same conclusion, the consistency of the observations became difficult to dismiss. The signal detected by NASA's Deep Space Network, combined with independent verification from other observatories, pointed toward a phenomenon that did not align with conventional expectations. While further analysis was necessary to fully understand the nature of the emission, the initial findings established a clear starting point for deeper investigation. At this stage, the focus shifted from identifying whether the signal existed to understanding how such a structured emission could be produced and maintained. The presence of a coherent, directed particle stream over such a long distance introduced questions that extend beyond standard cometary science and into broader considerations of physical mechanisms, energy sources, and structural stability. To understand why the observations surrounding 3I, Atlas, are considered unusual, it is necessary to step back and examine what the object itself represents and why it has drawn sustained attention from the scientific community since its discovery. Identified on July 1, 2025, 3I, Atlas is recognized as the third confirmed interstellar object to pass through our solar system, following earlier detections such as Oumuamua and 2I, Borisov. Unlike typical comets that originate within our solar system, interstellar objects arrive from outside, carrying with them material formed under entirely different stellar conditions. From the beginning, 3I, Atlas, followed an unusual trajectory. Its path entered the inner solar system at a steep inclination of approximately 87.63 degrees relative to the ecliptic plane, meaning it was not aligned with the general orbital plane shared by most planets. This alone made it noteworthy, as interstellar objects do not typically conform to the familiar orbital geometry observed among native solar system bodies. Its approach was direct, crossing the system rather than circulating within it, which is consistent with an object passing through rather than being captured by the sun's gravity. However, what truly set 3I, Atlas, apart was not just its trajectory, but its behavior after entering the inner solar system. For a period lasting over 7 months, the object exhibited what researchers described as thermodynamic silence. During this time, it absorbed significant amounts of solar radiation without showing the expected signs of mass loss. In standard cometary physics, increased exposure to the sun leads to heating, which in turn causes volatile materials such as water, ice, and other frozen compounds to sublimate. This process typically produces a visible coma and often a tail formed by escaping gas and dust. In the case of 3I, Atlas, none of these expected features were observed during that extended period. The object appeared dark and dense, with a metallic-like reflectivity in observational data, and showed no measurable shedding of material. This absence of activity led to ongoing discussions within the scientific community, as it challenged assumptions about how interstellar objects respond to solar heating. The situation changed abruptly on March 24, 2026, at approximately 3:14 UTC, when observations recorded a sudden and significant thermal event. Data from the James Webb Space Telescope, specifically using its near-infrared camera, NIRCam, detected a rapid spike in thermal emissions from the object. This spike occurred within milliseconds and marked the end of the object's previously inactive state. Unlike gradual cometary outgassing, which typically develops over time as internal pressures build, this event appeared instantaneous and highly structured. Instead of producing a diffuse cloud of expanding material, the object emitted a linear projection of ionized plasma and particulate matter. The emission formed a geometric structure rather than a randomly expanding distribution, suggesting a level of directional consistency not commonly associated with natural sublimation processes. Measurements indicated that this emission formed a stream, approximately 14,000 kilometers in diameter, maintaining parallel boundaries over vast distances. This means that rather than spreading outward, the material remained confined within a defined cylindrical region. In physics, maintaining such a structure in the vacuum of space would require forces that counteract the natural tendency of particles to disperse. To better visualize the difference, consider how a pressurized fluid behaves when released into a vacuum. Under normal conditions, the material would expand rapidly in all directions, losing coherence almost immediately. Yet, in this case, the emission maintained its shape, suggesting that some form of confinement or guiding influence may be present. The consistency of the observation was not limited to a single instrument. In addition to the James Webb Space Telescope's infrared detection, other observational platforms contributed to confirming the event. The European Space Agency's Gaia spacecraft provided independent verification of the object's trajectory and associated gravitational effects, while the ALMA Observatory analyzed the electromagnetic signature of the emission. Each of these systems uses different methodologies, yet they all reported results that aligned with the same general conclusion. The emission event was real, and it exhibited properties that required further explanation. At this stage, scientists began focusing on whether any known natural mechanisms could account for such behavior. While cometary outgassing is well understood, the formation of a structured, cylindrical emission over such a large scale is not something that current models predict. This led to further examination of variables such as internal composition, rotational dynamics, and possible magnetic influences that could affect particle motion. The combination of an initially inactive object followed by a sudden, highly structured emission event marked a significant shift in how 3I Atlas was being studied. Rather than behaving like a typical comet that gradually becomes active as it approaches the Sun, this object transitioned from a dormant state to a highly organized emission pattern in a very short period of time. This transition became a central focus for ongoing analysis, as researchers worked to determine whether it could be explained through known physics or whether it pointed to gaps in current understanding. Following the initial detection of the structured emission event, researchers began to analyze the internal dynamics of the particle stream in greater detail, focusing on whether its properties could be reconciled with known physical models or whether they indicated something fundamentally different from typical cometary behavior. Data gathered from multiple observatories, including infrared and electromagnetic measurements, provided a clearer picture of how the emission evolved over time and how consistent its structure remained across vast distances. One of the key observations was that the emission did not disperse in the way a conventional gas or dust cloud would. Instead, it maintained a highly confined cylindrical shape, with a measured diameter of approximately 14,000 kilometers and boundaries that remained nearly parallel over millions of kilometers. This level of structural stability is not something that naturally occurs in a vacuum without an external influence acting to contain or guide the particles. The importance of this observation lies in the comparison with standard cometary outgassing. When a comet approaches the Sun, heat causes volatile materials to sublimate, releasing gas and dust in a manner that expands outward in all directions. This results in a coma that gradually diffuses into space and, under the influence of solar wind, forms a tail that generally points away from the sunday. The dispersion is inherently chaotic, influenced by rotation, surface irregularities, and uneven heating across the comet's nucleus. In contrast, the emission from 3I Atlas showed a high degree of directional coherence. Instead of expanding radially, the particles remained aligned along a narrow vector, suggesting that their motion was being constrained in a way that counteracts the natural tendency to disperse. To understand this behavior, scientists examined whether magnetic forces could play a role, since ionized particles can be influenced by electromagnetic fields. In laboratory and astrophysical contexts, magnetic fields are known to guide charged particles along defined paths. However, maintaining a stable, large-scale magnetic structure capable of confining a particle stream across interplanetary distances would require sustained field strength and stability far beyond what is typically associated with natural celestial bodies. Estimates based on the observed coherence suggest that a magnetic field on the order of several Tesla would be necessary to maintain such confinement over time. This raises important questions about the source of such a field, if it exists, and whether any natural mechanisms could generate and sustain it within an interstellar object. While magnetic fields are common in stars and planets, their intensity and configuration vary widely, and they are not typically associated with small, isolated bodies like comets. As a result, the observed structure of the particle stream does not easily fit within existing categories of natural magnetic phenomena. At the same time, the consistency of the emission across multiple observational platforms reinforced the reliability of the data. Measurements from infrared instruments, optical telescopes, and electromagnetic receivers all indicated similar structural characteristics, suggesting that the cylindrical shape was not an artifact of a single measurement system, but a real feature of the emission. Researchers also considered the possibility that internal processes within the object could contribute to the observed behavior. For example, variations in surface composition, internal pressure buildup, or rotational dynamics could potentially influence how material is released. However, none of these factors alone are sufficient to explain the sustained coherence of the stream over such long distances without some form of guiding influence. As the analysis progressed, attention turned to the possibility of non-gravitational forces acting on the emitted particles. In cometary science, non-gravitational forces are known to arise from outgassing, which can produce small but measurable changes in trajectory over time. These forces are typically irregular and depend on the distribution of active regions on the comet's surface. However, in this case, the emission appeared to follow a highly consistent and directed path with minimal deviation from its initial alignment. This consistency was further highlighted by the precision of the stream's orientation relative to the solar system. The emission was observed to align along a vector that intersects regions near Earth's orbital path, maintaining a deviation of less than 0.03 degrees. Such precision, over millions of kilometers, is not typically observed in natural dispersive processes, where small variations tend to accumulate and produce broader spread patterns. To verify these findings, multiple independent observatories cross-checked their data. The NASA and the European Space Agency both confirmed the consistency of the observations using different analytical methods. Additionally, the ALMA Observatory contributed high-resolution electromagnetic data that supported the conclusion that the emission maintained a coherent structure rather than dispersing randomly. At this stage, the scientific focus shifted toward understanding the stability of the emission over time. Maintaining a confined particle stream requires not only an initial force or mechanism to generate the emission, but also a sustained process to preserve its structure. This introduces questions about energy sources, control mechanisms, and the physical limits of natural systems in extreme environments. The combination of observational consistency, structural coherence, and directional precision has made the particle stream from 3I Atlas a subject of ongoing investigation. While researchers continue to explore possible natural explanations, the data has prompted deeper examination of the underlying mechanisms that could produce such a phenomenon, particularly in the context of known physical laws and astrophysical models. As the investigation into 3I Atlas progressed, scientists began focusing less on isolated observations and more on how the system evolved over time, especially in relation to the structure and behavior of the particle stream. With multiple observatories contributing data, including instruments operated by NASA and the European Space Agency, a clearer timeline of events started to emerge, revealing that the emission was not static, but dynamically changing in ways that required careful interpretation. One of the first notable developments occurred approximately 24 hours after the initial detection of the cylindrical emission. At around 3:14 UTC on March 25, instruments at the ALMA Observatory recorded a sudden and significant shift in the composition of the particle stream. Prior to this point, the stream contained a mixture consistent with standard cometary dust and silicate materials. However, the new readings showed a marked decrease in silicate content alongside a sharp increase in highly charged metallic ions. This transition was not gradual, as one might expect from a slowly evolving outgassing process. Instead, it appeared to occur abruptly, suggesting that some internal mechanism within the object may have altered the nature of the emission almost instantaneously. In natural comet behavior, compositional changes typically reflect variations in surface layers exposed to solar heating, but these changes usually unfold over longer periods and are influenced by rotation and uneven heating. The sudden shift observed in 3I Atlas raised questions about whether the emission process was being influenced by more than just passive thermal effects. The consistency of the cylindrical stream remained intact, but the internal composition of the emitted material had clearly changed. This indicated that whatever mechanism was responsible for the emission had the ability to modulate not only the direction and coherence of the stream, but also its chemical makeup. Following this compositional change, another significant behavior emerged. Approximately 48 hours after the initial venting event, the emission began to exhibit a pulsing pattern. Rather than maintaining a continuous and steady outflow, the particle stream started to turn on and off at regular intervals of about 23 seconds. Each pulse delivered a consistent volume of material, estimated at roughly 33 billion tons of ionized particles per cycle, all directed along the same vector. This pulsing behavior introduced a new layer of complexity to the analysis. In natural systems, periodic emission can sometimes occur due to rotational effects or localized surface activity. However, the regularity and precision of the observed pulses suggested a level of control that is not typically associated with random or chaotic natural processes. Each pulse was nearly identical in both duration and output, indicating a highly stable underlying mechanism. To evaluate whether such a phenomenon could arise naturally, researchers considered known sources of periodic activity in comets, such as rotational modulation or localized jets, that activate as different regions of the surface are exposed to sunlight. While these processes can produce variability in emission, they rarely result in uniform, clock-like intervals with consistent output across each cycle. In addition to the timing of the pulses, the energy required to sustain such emissions became a critical point of analysis. Producing and accelerating 33 billion tons of ionized material every 23 seconds would require an energy source far beyond what is typically associated with solar heating alone. Solar radiation, while significant, does not provide the kind of sustained, high-density energy input needed to drive such a system at this scale. This led scientists to consider whether an internal energy source might be involved, one capable of regulating both the timing and magnitude of the emissions. In astrophysical contexts, energy generation mechanisms can vary widely, from nuclear processes in stars to residual heat in planetary interiors. However, none of these are known to operate in a way that produces precisely timed, high-volume pulses of ionized matter from a small interstellar object. Another important observation was the stability of the emission direction during this pulsing phase. Despite the intermittent nature of the output, the overall alignment of the particle stream remained consistent, continuing to follow the same vector that intersects the region near Earth's orbital path. This indicated that the pulsing mechanism did not affect the orientation of the emission, but rather modulated its intensity while preserving its trajectory. Throughout this phase of analysis, researchers continued to rely on data collected from multiple independent sources to confirm the reliability of these observations. The combination of infrared measurements, electromagnetic signatures, and trajectory tracking helped ensure that the detected patterns were not artifacts of a single instrument or methodology. Instead, the convergence of evidence from different observational platforms supported the conclusion that the pulsing behavior was a genuine feature of the system. As the object continued to move along its trajectory, the timing of the pulses and their alignment with the solar system became a focal point for ongoing monitoring. Scientists recognized that if the pulsing pattern remained consistent, it could provide additional insights into the internal dynamics of the object and the mechanisms responsible for maintaining the emission structure. At this stage, the analysis had progressed from identifying a single anomalous event to documenting a sequence of behaviors that included a sudden emission onset, a compositional shift, and the introduction of a highly regular pulsing pattern. Each of these elements contributed to a more complex picture of 3I, Atlas, one that continues to be studied as new data becomes available and as researchers work to determine the underlying causes of these observed phenomena. As observations of 3I, Atlas continued to accumulate, researchers began focusing on the broader physical implications of the object's behavior, particularly the nature of the material being emitted and what it reveals about the object's internal composition. With instruments across multiple observatories contributing data, including those operated by NASA and the European Space Agency, attention shifted toward the spectroscopic signatures embedded within the particle stream. On March 27, at approximately 6:15 UTC, the ALMA Observatory detected spectral data that introduced a significant development in the analysis. The readings indicated the presence of refined heavy metals within the emission, including isotopic signatures associated with titanium 50 and uranium 235. These elements are not typically associated with standard cometary compositions, which are usually dominated by water ice, carbon-based compounds, ammonia, and silicate dust. The detection of such isotopes raised immediate questions about their origin and how they could exist in a comet-like object. In conventional astrophysical models, comets are considered relatively primitive bodies composed of material that has remained largely unchanged since the early formation of the solar system. They are not expected to contain concentrated deposits of heavy, refined elements, especially in isotopic forms associated with nuclear materials. The reported concentrations were also notable. According to the spectroscopic analysis, the levels of these metallic isotopes were significantly higher than anything previously recorded in known celestial objects. Estimates suggested concentrations up to 10,000 times greater than typical background levels observed in interstellar or cometary environments. This discrepancy prompted further scrutiny, as such enrichment is not easily explained by natural formation processes alone. In response to these findings, researchers conducted cross-verification using multiple independent data sources to rule out instrumentation error or misinterpretation. Spectroscopic instruments at different observatories operating under distinct calibration systems produced consistent results. This consistency strengthened confidence in the data, indicating that the detected isotopic signatures were not anomalies caused by a single measurement system.